All right, well, thanks for the introduction, Ian. I do realise that I'm standing between you all and the bar, so as a Scotsman who actually had a alcohol-free January for charity, I must add, I can fully sympathise with the need to crack on here and get to the bar. So my theme of my talk today is actually broadband seismic. Now, one of the previous speakers referenced that today. It is a very hot topic in onshore and offshore seismic at the moment. And I want to just explain a little bit about what we've been doing in terms of broadband seismic from an equipment manufacturer's perspective. There are a lot of challenges involved in putting together equipment that will allow the E&P companies to collect the best broadband data. So I want to talk about a little bit about the benefits that broadband is delivering to the oil companies, and then a little talk about our portfolio, which includes sources, vibrator sources, digital sensors, and cableless and cable systems as well, and just talk about some of the challenges involved in that and some of the solutions that we've come up with. And I would point out, I come here regularly, and there's always a lot of talk about cableless systems. People get very interested and excited about it. I would point out to everybody here that right now, cableless systems take about maybe 10% of the total channel capacity in the seismic market. So 90% of acquisition right now is still cable-based. So just a bit of context there. So, what do we mean by broadband, first of all? So, I think, if you like, consider legacy acquisition. You'd be talking about a range of frequencies, roughly between 10 and 80 hertz would be a standard kind of acquisition. Nowadays, we're pushing that in both sides. We're going down to getting close to 1 hertz. We've been involved in some projects in the Middle East where we've been generating some energy at 1.5 hertz. So that's becoming more and more prevalent, and even in the higher frequencies, particularly in areas like Canada, where the shales and the sands, we're going up to what, 200 hertz, 200 plus hertz, and beyond. So broadband is really pushing the borders of that acquisition. And why is the interest in broadband? Well, obviously, low frequencies have a lot of benefit for deeper targets, things like carbonates, where you really need to go deep. High frequencies are good for vertical resolution, so anything like thin shales, thin channel sands, that's where high frequencies really have a benefit. And I guess exploration nowadays is going into more and more complex geology. So whatever we can do to improve the quality of the image is going to be of benefit. And also there is a technology used and is becoming more and more widely used. Full waveform inversion is a technique which actually we see as moving from almost a lab kind of environment to more of a mainstream part of the processing flow. This little graph here, it's a little bit fuzzy, apologies for that, taken out of the leading edge, I think. It actually shows the number of papers published that talk about waveform inversion or full waveform inversion over the last few years. So you can see there's been a tremendous amount of interest in this. The development of computing, techniques like reverse time migration, the computing performance that's come about from those advances has gone right into this process here. And broadband plays right into that process too. By acquiring data with a much wider band, we add more octaves, and we really sharpen this seismic wavelet definition. That really helps stabilize the inversion process. Also, by acquiring low frequency data natively in the survey, we remove the need to use well logs, or which are more sparse typically for inversion purposes. So we're really getting a lot of benefit out of broadband through this inversion process, and creating a much more accurate initial velocity model. So now, just wanted to show you a little example of what data looks like when low frequencies are processed through it. This is some data that we've been very graciously given by a PDO from North Oman. And this is what we would call conventional data that was processed conventionally. And this is the same data set but processed with the low frequencies. So you can see this stunning improvement in data quality through the use of low frequencies. And over the last few years, there's been numerous examples showing this scale of improvement. So what's involved then in putting together a broadband survey? I think obviously it starts at the design stage. You've got to consider what offsets you need, how densely I'm going to sample this project, what kind of fold am I going to need? Am I going to need to do wide azimuth? So the design function is critical to getting your broadband project put together. And then once we've got the design, we put that into the acquisition phase. And the acquisition phase requires the right kind of source to generate the maximum broadband energy with the lowest distortion. We need a sensor that can capture that data adequately over a very wide band and in an efficient way. And then we need a system, an acquisition system, that can bring all that together in a very high density, high channel count fashion with the highest kind of productivity you can achieve. And then of course there is things like field QC, and then further down the line processing, interpretation with inversion and so on. But the focus for me today and for our company INOVA as an equipment supplier is this acquisition piece, and we provide elements of all three pieces here. But I think the key takeaway is that broadband is a methodology right across design and acquisition and processing. But in terms of acquisition, it's really important that you consider all three elements together in an integrated fashion. So I want to talk about sources first. Here's a vibrator. To get that to generate very low frequencies, there are a number of challenges that we have to face. First of all, we have the basic principle of Newton's law, which we can't do anything about. Basically, force equals mass times acceleration. So, as an example, if you wanted to create something like 30,000 pounds of force at 1 hertz, you would need a stroke of about 50 centimeters, 60 centimeters to generate that energy. So, Newton's law can't be defeated, so we have to work our way around that and work within the practicalities and limitations of that. So there are significant mechanical constraints that Newton's law causes. Also, this is the base plate here. Now the base plate is a metal construction. It has to be very rigid as possible. It has to withstand some serious strain. What we've found with conventional vibes is that as soon as you get into sort of high frequency vibrosize, these things start to flex. They start to, like little birds flapping their wing. They get out of control. And what that means is you cause a lot of distortion, you get a lot of inefficiency, and you'll lose the energy that you're looking for. Hydraulic systems as well. They need a lot of very high power hydraulics to drive these things. And they're actually a system which have a bandwidth themselves. And they have all sorts of problems, again, both at the low and the high frequencies. So we have to overcome them. Harmonic distortion, another problem, again, especially at low frequencies. The generation of harmonics to contaminate your data. How do we control that? How do we attenuate those? Sweep design, you know, can you take just a normal sweep design and throw it into a very wide bandwidth sweep? It doesn't work. You have to take into account the fiber size itself, the machine and what it's trying to do, and design the sweep appropriately. And then of course the machines have got to be reliable and work in all kinds of environments. So you know, developing a 1 Hertz vibe is a serious world-class challenge in all senses, electronics, mechanics, hydraulics. This is a very, very difficult challenge. So what we've been doing, just going to give you an example of some of the improvements we've made with our vibes. This is the improvement that we've seen by a completely new base plate design. So we basically redesigned our base plate, completely new mechanical structure, strengthened it, new materials, new weight, and so on. And you can see the difference that it makes. And the green is what we would call our sort of legacy base plate performance. And you can see that it works pretty well in this kind of 10 to 80 Hertz band. That's what it was designed for at the time. But you start pushing that up to 120, 150 Hertz, and you get a lot of instability, both in terms of phase and amplitude response. So you can see here the improvement that this new base plate design that we have has made to the performance of the system. Here's another example where I mentioned hydraulics earlier on. Now I'm not a hydraulics engineer, but I think you can see here the blue graph is again what we saw with our legacy vibrators, what they were doing, what their hydraulic system, how it was behaving. This is what we saw. So again, I think you can see the problems that we get. Here at low frequency, the pressure just drops, and here at the higher frequency, you get these ripples and cavitations. So that's not good for a broadband system. So we have completely re-engineered our hydraulic system, and you can see the results here with the red graph here, showing the improvement that we've made to our hydraulic system. And here's sweep design. So we have our newest vibe is what we call the 364, and our legacy vibe is called the 362. So just in case you see those on the diagrams. But on the left here, we see this is basically a customized low frequency sweep that we've programmed into our vibe, and this on the bottom is our like a standard linear sweep, a conventional sweep. And what we track here is the pilot, which is what we intend to put in the vibe, and then we actually measure the ground force created. So that's what actually went into the ground. So you can see that with the conventional linear sweep, you get quite a divergence of what you think you were putting into the ground compared with what actually went into the ground. Whereas with our custom sweep, we have a much closer tracking. So getting the sweep design right is another critical piece. And here is an example of harmonic distortion. So on the left, we're looking at a linear sweep, and on the right, we're looking at a special low-frequency sweep. And on the top is what we see with just standard controllers, standard source controllers. You can see the fundamental and then the various harmonics being created there, and you can see that on both of the A slides at the top. Now, what we've implemented in our VibPro source controller is some control algorithms in our firmware and in our electronics, which basically attenuate that harmonic energy. And you can see that in the B plots where we've reduced these, batteries going here I think, we've reduced the harmonics on both the linear sweep and on the low frequency sweep. So it's an important part of, again, data quality. And here is overall what we see when we put all of these things together and we compare the conventional vibes against the newer vibes. And what we've focused on here is that 1 to 8 hertz band. So this is the legacy vibrator here, the new vibrator here, and you can see this very significant improvement in energy as measured by downhole geophones. Again, particularly at the low frequencies, but really across all the band. So very significant improvements there. So in terms of broadband source, you know, we've been working hard over the last few years on this R&D, looking at all of these areas. And broadband acquisition really starts with the source, so it's really critical to get that right. You want to get the maximum energy into the ground with the lowest possible distortion. And as I said, these vibes, they've been used and are being used widely in the Middle East in particular, working at 1.5 hertz, 2 hertz routinely. So that's source, and I want now to talk about sensors. So if you think about sensors for broadband acquisition, what are the challenges there? Well, again, you are talking about recording a very wide band. What do you want there? You want to have a very flat and stable response from your sensor over the widest possible band. You don't want to see any attenuation of high frequencies. You want to have low noise and low distortion. And you want to be efficient in terms of your operation, your operational model. You don't want to be lugging around lots and lots of geophones and with all the weight and so on that goes with that. You want this to be simple to process, and you want it to be robust enough to survive the bashing that a crew will normally apply to the equipment. And yeah, why not make it very low cost and with very low power consumption? So one of our main kind of R&D strengths at INOVA is in MEMS technology. And we feel that MEMS, digital point sensors using MEMS technology, is a very good solution for broadband recording. You know, the MEMS has a very wide bandwidth. We can record almost 8 octaves of bandwidth with MEMS. Here's a plot here of 2 of our new 1C MEMS sensors, showing its response between 2 and 1200 hertz. So very flat and stable performance. Some of the benefits of MEMS: you don't need to compensate the data below the natural frequency of geophones, the 10 hertz and 5 hertz problem. The natural frequency of MEMS is way up at the kilohertz range. Dynamic range is maintained throughout that bandwidth, so you don't see any drop-off of dynamic range as you get down into lower frequencies. With a single point sensor, you don't have these array attenuation problems that tend to dampen your high frequencies or you know, alias your signal and noise. And because it's a point sensor, you don't have any of the linearity kind of effects with array and directional issues. And then you know, these MEMS sensors are also very robust. They're lightweight. They're easy to handle. So you can get through a spread. You can move a spread very quickly. They can handle things like overload conditions very easily. They can switch into different scales, which a geophone can't really do. And because they're discrete electronics, they have a fixed specification. They either work or they don't. They don't wear, they don't age over time. And systems nowadays can self-test these devices very quickly. They're also immune to electrostatic pickup, overhead lines, and so on. And of course, they can be operated in a continuous recording mode. So One of the developments that we've made recently is a new sensor. This is it here, without the spike. Airport security get a little bit edgy about this sort of things. This is a device here. It's what we call the AccuSize sensor. So it's a 1C MEMS sensor. Those of you that know the vector size sensor, it has the same MEMS chip in here, but a completely re-engineered control electronics around it. Completely re-engineered housing as well. And it's a very lightweight device. It weighs only 175 grams. The power consumption of the device is 85 milliwatts, so huge reduction in power compared to previous three-component versions of this system. It's a simple two-wire telemetry. We can handle different sample rates. We can also deploy this as a string of 3 sensors on a string. But each sensor is an independent point sensor station. So it means that we can get quite efficient integration with our acquisition systems. So this is how it integrates. I've shown the example here of it integrating with our cable system. This is our G3I cable system. These are the electronics, the ground electronics. This is a standard 220 meter R-line cable with 4 takeouts, and there you can see the 3-string of the SL11 connected here. So we have 12 sensors driven off one of these units. So this lends itself to very high density sampling. The power is very low. We can drive 108 stations, 1C digital stations off a single standard battery, and of course the ratio of channels to ground electronics is very good. So from the contractor's perspective, it's a very cost-effective solution to deliver the high density spatial sampling, which again is a key part of the broadband acquisition process. So here's another example of if we just take a geometry. We've just created a geometry here. The key thing to note is the receiver line spacing, the receiver spacing, I beg your pardon, 60 meters between receivers here, giving us a receiver density of just over 23 per square kilometer. So if we set up this project using our G3I system, for example, we would use 3,813 pieces of ground electronics, the RAMs, over those 31 lines, traditionally with analog sensors. But if we went with the digital SL11 and stuck 12 of these in per RAM, what we can actually get now is a very high density, 20 meter receiver spacing. We've increased our receiver density to over 70 traces per square kilometer, and from the contractor's point of view, we've actually reduced the amount of ground electronics that he requires to do that by 13%. So the economics for a contractor's perspective, very good, and the data quality aspect from the oil company's perspective is also very good. So that's what we've been doing in sensors. So again, the key thing here is what you need to do for bandwidth, for broadband acquisition, is capture that broadband energy with a wide bandwidth, low power and low cost sensor. And finally, the final sort of piece here is acquisition systems. So we've had a lot of talk about cableless and cable systems. As I mentioned earlier, cable systems do still, fortunately or unfortunately, dominate the market hugely. The challenges, though, for acquisition systems in terms of delivering broadband data are, well, you've got to have systems, a combination of systems that are going to work in all kinds of terrain with all kinds of sensors and all kinds of environments. They've got to be reliable. They've got to have a very high uptime, They've got to support these high density operations, high fold, wide azimuth, and they've got to be able to support these operations in a very efficient manner. So all of the high productivity techniques that are allowing oil companies to really get a huge production, you've got to support them. So we have two things, two systems that fit into this portfolio. Hawk is our cableless system. Now, in complete contrast to the previous two speakers, we don't really care about radio infrastructure at all. I think we've heard enough about the complexity and the risks associated with real-time radio systems. So we've gone the other direction, really. We've gone for a simple, rugged, autonomous node. This is a device that can handle any kind of sensor, digital, one channel, 3 channels, analog, geophones, all from the same box. You can drive as many different types of sensors as you want, but from one box. Very simple operation. GPS for timing, and yeah, we have some Wi-Fi for short range status QC. So a contractor can take a vehicle, any vehicle he wants, or a helicopter, or a person, walk past the system and get some QC and check that the system's working correctly. Opportunistic QC is what we call that. And this has unconstrained channel capacity. The only limit on channel capacity with this system is how much computing power you have at the back end to handle all the data. That's the only constraint that we have. And we're using this system heavily in the US. We've got several crews now running 30,000 channels of Hawk, and a crew size typically there is about 60 to 70 people. So they are getting serious productivity, very high capacity with this system. And G3I is our cable system. And G3I, again, some of the key features here. We've got to make sure that the weight, overall weight, is low. So we've concentrated on getting our power consumption very low, which means fewer batteries and less weight. Our system is now capable of supporting over 100,000 channels. We recently did a test in China, which I'll just show you in a minute, where we had over 50,000 channels in real time operating in China. And of course, all of the high productivity vibra-size techniques are supported with real-time QC and correlation. And this system is specifically designed for easy repair and service in the field. So this is a project here that we did in China in October, November of last year. We went out to the Xinjiang province, the Kalamai oil field, the number 4 producing field in China, discovered in 1956. Mr. Mao was very happy about that, I'm sure. This is where the survey was. It was a kind of combination of gravel plains, nice for high productivity cable acquisition, but there was lots of little kind of sabka areas and also what the Chinese called wind eroded structure that you can kind of see in this image here. Here are the parameters that we had. You can read those. It was fairly broadband. Started at 3 Hertz. It was a DS4 operation, which is distance separated, simultaneous slip sweep. And we used 16 vibes separated by 14 kilometers to acquire that data. This one was actually using geophones. Here's just a sort of cartoon to show the acquisition scheme. We had a 36 line patch with 33 kilometer lines, and this was the shooting kind of operation here. So we had salvos of 6 VPs shooting orthogonally into the patch with a 36 line recording scheme there. DS4, as I mentioned earlier. And basically the Vives were organised in 2 groups by 4 kilometres and 2 groups side by side. And they basically moved their way up this patch, acquiring all the data as they went along. So we had between 48 and 54,000 channels at 2 milliseconds in real time, with correlation and with QC on this project. The line crews also, some numbers there in terms of their productivity, rolling about 5,000 channels a day, or 336 per crew maximum. So that gives you an idea of the productivity. So this was, we believe, the largest live channel count system operated in China. We covered almost 400 square kilometers in a month. And one of the remarkable things from our point of view is this job required a 2-week mobilization and a 1-week startup, and then we were shooting with 50,000 channels in real time. Production peaked 10,872 VPs in a day. I mentioned the receiver roll here. So we were recording something like 250 gigabytes per hour. So that was Xinjiang, and we'd like to thank BGP Crew 278 and the Xinjiang Oilfield Company for permission to show this information and allow us on the project. So hopefully, I've explained that high performance and high capacity acquisition systems are also a really key part of the broadband story. We've seen the source technology, the improvements in source technology, getting that energy into the ground. Digital sensors that we talked about, we think are ideal for broadband recording for lots of reasons. And then pulling it all together, high performance acquisition systems. So that concludes my talk. I'd also like to thank PDO for permission to show the slides with their low frequency data as well. So, thanks.
Thanks very much indeed, Andy. So we're up to date with marine systems, new technologies, fiber optics and land systems of all types. So any questions for Andy? We have a few.
Andy, Daniel Finn for Silixa. Thank you for the informative presentation. Can you talk a little bit about the specific argument for dense 1C versus kind of sparse 3C layouts? I'm sure you encounter customers who want to push to have as many directions as possible, and so saying go back to 1C, you must have an argument for that.
Yeah, 1C. I mean, I think it's no secret that multi-component data, multi-component processing as a market has kind of stalled at about 5% of the overall market over the last, 15 years or something. So it's no secret that that's been a struggle. There are still areas. Canada is particularly strong with 3C at the moment. Even in North America, there's a lot of 3C work going on there. So there are niches where 3C is very well regarded and is used with some great results, but it just hasn't taken off. And the big problem with 3C has always been the time it takes to process that data, the bottleneck, and getting the final image through. So we've recognized that, and that's why we've been working on this, to create a 1C sensor, because a lot of people use 3C and they just use the P-wave, the 1C data. They liked it a lot, but the overhead of having 3 channels, the power, the cost, wasn't doing it. So that's why we developed this, and we really focused hard on the power and the cost, so that we could integrate it and amortize it effectively.
I have a question, Andy. Does that machine there, does it know which way is up, or does it have to be planted vertically?
No, it knows which way is up, and the systems alerts the systems.
So actually, it's probably got 3C in there.
Yeah, well, it's. Yeah.
Okay. Well. Okay. Any other questions for Andy? Okay. Well, thanks very much again, Andy.
All right.